So the next talk will be about Rust and given by Arnaud Golfouse from Inria.
Okay, so I'm a PhD student working with Jacques-Henri, Jourdan, and Armaël Guéneau, and I'm here to talk to you about how we verified union-find and persistent arrays in Rust. So in Rust, you have this interesting principle that's called the shared XOR mutable a lot of the time, and that brings us some very strong guarantees about aliasing of pointers. So here's an example of a program that has pointers. It has mutable borrowers, which are checked by the compiler. And so we are assured that these two pointers do not alias this x and y. So if you write to x and then y, you know that the write to y did not influence the value of x. And so this assertion will always pass. In fact, if you try to make those two pointers alias by passing the same pointer twice, the compiler will complain, and it will produce a compile error. If you do want to alias, you can use row pointers and some unsafe code. And so you code basically the same function, but you replace ampersands with stars. And you add some unsafe, and then it works, except of course it will crash at runtime because the assertion no longer passes. As much as possible for our purposes, we'll try to keep doing stuff in this world because it's much easier for verification. So our verification tool is Crusoe, and it actually uses these guarantees that the shared XOR principle gives us. So, for example, here's a specification for this function f. It doesn't have a precondition because the pointers are already separated and there's nothing to assert. But it does give us a very simple postcondition for the writes we did. So like it says here that the x pointers receive the value 1 and the y pointer receives the value 2, and that's it. With this caret operator that says this is the value we've written into the pointer. But sometimes we do want to verify structures that are more complicated than that and do use shared mutation with, for example, row pointers. An example of such a structure would be union find. In union find, you categorize elements into sets. So for example, here we have A, B, C, and D that are originally in two sets. And you can do some union operation on elements to merge their set together. So here we could union B and D to get this full set of the 4 elements. And you could implement that with pointers by saying that B points to A, D points to C, and the union just changed the pointer, and so the sets are represented by a single element by following the pointers. So when you follow the pointer, you get the sets that they belong to. And here we can see that it explains why it's a bit hard to reason about that, because if you try to do this find call, so you find the element, the set that A and C represent, before the union, those two are different. After the union, they are in the same set, so the call will be equal, except of course the union operation does not talk about A or C at all. So you have a very non-local behavior here, and it's quite difficult to reason about. So that's mainly why we want to stay in the easy world of borrows. So if you want to specify this program with pointers, you can take inspiration from the implementation without pointers, and we try to inspire yourself with that. So without pointers, you usually use an array. You have this big array, which is a vec in Rust. And the elements are no longer pointers, but they would be indices in this array. And this is easier to reason about because you pass the whole state of the union find to each function. So each find, each union call will get this whole array. And so reasoning about it becomes much easier. To do that with pointers, instead of this array, we'll use a piece of ghost state, big ghost states that talks about all the pointers that our union find is currently managing. And we'll have some relation between the pointers in the program world and the ghost states in the ghost world to make this all work. And in order to get back our guarantees about aliasing, we need to find a way to borrow check this, to have the compiler borrow check this ghost code, this ghost object. So that's what we did. In this talk, I will present how we adapted this notion of ghost state with ownership, which was first implemented in Verus, and we implemented it in Creusot with our specific way of doing things. In particular, we can support all the pointers, usual pointers operation. And so usually when you verify a program with pointers with Creusot, the ideal, and in this case what we will do, is only add ghost code. You keep all the other operation, and you add ghost code in the middle, and it should work. And in this case, we will verify how to do, we will see how to do union find with that. So, so pointers. So to get our guarantees, we cannot use pointers as is, because we just said that they introduce a lot of aliasing and mutation at the same time, so that's not possible. So you cannot dereference pointers. If you do that, the tool will just yell at you. Instead, you use this this composed type, which is composed of a ghost and then the pition. And the first part will be about erasing this object from the normal code, so that it does not incur overhead. So, yeah, so when you have a ghost object, you can manipulate it. From the point of view of the verification tool Creusot, it logically contains the value that it envelops. So you can talk about it in the specification. Here in this requires, you can say that its value is a certain number, for example. And in order to get our rules of ownership back, this does have the same ownership as the type it contains. So here it's a box are non-duplicable, so this ghost object is also non-duplicable. If you try to, the compiler will raise an error. On the other hand, in the normal code, in the code compiled by the compiler, this type is compiled down to unit, and units are completely erased in Rust, so it does not incur any overhead. Then, inside this ghost, I said we will put a pition. So this pition object should be conceptualized as a points to of separation logic. So there's on the left there's a pointer, and on the right there's the value you want to store in there, because it will track the value in the ghost code. So you can access those two parts in any specification you want. And in order to use that in the code, in order to use pointers, you will need to combine the two. So you will need three operations. You will need to create pointers, to read from them, and write from them. So these are these three operations. Each time you allocate a pointer with this API, you get also an additional object, which we call the permission, which is a ghost of pition. Each time you want to read, you need to use this asref, and each time you want to write, you need to use this asmut. And I'll focus a bit on the specification of this asmut function. So it looks like this. This is straight from the standard library of Creusot with the same specifications. And I also wrote an example in order to see what this specification mean a bit more. It makes them a bit more easy. So at the start, when you want to get, so this function takes a pointer and it will translate it into a mutable reference by using the permission. So the first thing, the only thing it requires is that the pointer you're using is actually the right one for the permission. So this is this first equality this requires, and it corresponds to this equality in the code. And then it gives you three post-conditions. The first one being that the pointers did not change. The pointer associated with the permission did not change. And then we can talk about the value that you get into the borrow when the value that is originally inside the borrow is indeed the one that was in the points to. And then we can use a bit of Creusot specifics about these caret operators to say that the last value that you write into the borrow will become the new value of the permission. And so in this example, we can get the specification that we want, which is that the value was incremented by 1. And so, okay, so now we have all these pointers. We can start to talk about union find. So these are the types and the type invariant that union find will use. So the first type is the data type, the type that will actually get compiled into the program. It's sometimes either you're at a root or you are linked to another element that you need to follow to find the root. And then you have this UF type, which will always be wrapped in Ghost. And that contains all the permissions that we defined so far. It maps them, so it contains this map. If you need to use a permission for a pointer, if you want to read a pointer, you need to index into this map, find the right permission, and then use it. To ensure that it's the right permission, you have this type invariant on this UF type. So it's defined as this logic here says that the function is usable only in specifications, and so you can use all sorts of logical operators like for all. And so it says if you contain if the pointer is contained in this permission map, then indexing it will get you a permission that has the right pointer. And then you can say some additional stuff about the value if you need to. If you would verify the actual program, you need to talk about the value as well. Now we talk about find, the find function. So the find function in program code starts like this. It's you take a pointer, you return another element as a pointer, and you of course start by reading it and trying to find if it's a root or linked to another element. The rest of the code will not talk about it, but the first is already interesting because we need to read this pointer. To do so, I said that we only will add Ghost code. So here's the proof. We just add a bunch of stuff around those pointers. We have the specification that says that the pointer is indeed managed by this big Ghost UF structure and that the return value is correct in the sense that it's a root. But mainly I'm interested in how we get this permission because we need to use as ref in order to read the pointer. And so we need a permission to do so. To get this permission, so this asks for a ghost of permission. We only have a ghost of UF. And recall that it's a map, so we need to do some additional operation in order to get this. So one thing I did not talk about up until now is that we also need to execute some ghost code in order to retrieve this permission and use it to read the pointer. So in this case, it would simply index into the map, and the rest will follow. And these ghost blocks, so these ghost blocks do have some restriction on them in order to not influence the normal run of the program. And here's a summary of all these restrictions, basically. So what it says is, each time you enter, each time you exit, the second line says each time you exit the ghost block, you wrap the result into this ghost object. And conversely, each time we want to use a ghost object, we will have to enter a ghost block. So you can't use this object outside of the ghost block. You can, although you can do whatever you want with it inside of it. As for normal programmable value, you can read them, but you can't write or move them into the block. And of course, you can't escape. You can't have control flow escape the block to the outside, as it would change the control flow of the program. So that's all the mechanisms we need to complete the proof. So I presented to you how we implemented ghost code with ownership in Crusoe with this ghost type and the ghost macro, and how did we handle pointer with this PTR own object, and we showed how to do the proof of union find. In the paper, we also added more mechanisms, in fact, in Crusoe, which are lifted from Iris, which are resource algebra, a combination of resource algebra and local invariant that allowed us to do a proof of persistence arrays as well. Those two proofs are in Crusoe's repository right here. Thanks.
We have time for a few questions. So I'll start. So you said that you took inspiration from Verus, right?
Yeah.
By adding ghost code like this, in this way that is borrowed check to Creusot, do you have new capabilities that Verus doesn't have?
We do because Verus in the start does not exactly have the same feature set. In particular, this function is not implementable in Verus, so it takes a pointer and translates it to a mutable borrow, and it does not exist in Verus because you cannot return mutable borrows. And so, yeah, basically around mutable borrows we have a bunch more functions that allows us to do a bit more things. Yeah.
Thanks for the talk. Maybe this is just in my head, but I think the average Rust user is maybe a little more into the language and the PL of the language itself than for some other languages, although maybe not at the level of a full theorist. How would you explain the significance of your results to someone who uses Rust in industry or casually?
If I were to sell it in some way to a Lambda Rust user, I would say that this is the thing that brought unsafe code to Creusot, basically. You could do some really small unsafe stuff, but the manipulation of, say, row pointers and also interior mutability is really is unlocked by this ghost code.
Maybe following up on this, so you said this brings unsafe Rust to Creusot, right? Last year, I think at PLDI, there was a talk by Sasha. I think that was about combining Creusot for safe Rust and Gillian for unsafe Rust, and Gillian is based on separation logic and Rust belt. Do you have a way to compare, let's say, this hybrid approach and your here this new version of Creusot?
Well, I would say the thing here is that we avoid separation logic per se. We only use the type system to encode some principles, but we do not explicitly reason with separation logic and iris and that kind of stuff. So it's more integrated, but maybe also the reasoning principles are a bit weaker. They have to be encoded into Creusot. Like this function is axiomatized in Creusot. It's not proven.
I'm not a Rust user, but I've tried to study Rust. I'm more of a C++ programmer, but I'm trying to take advantage of some aspects. I want to understand, this is my ignorance. Did you say that this ghost notation has no runtime overhead in production?
Yes.
Okay. And the second question is, does it in effect then give you another notation for doing essentially the same thing but without passing the entire aggregate and using indices?
Yeah, kind of, yes. That's the idea, is that you get a similar reasoning principle, not exactly the same because it's not an array here, it's like a map, but you get similar principles.
Then the benefit that I would see from this, if it exists, is that you could have two accesses to the same array as long as they don't overlap or the pointers are not. The point being, if that's not the case, what have you bought yourself other than another way to say the same thing? And if the answer is you've now taken something that was a big aggregate and you've turned it into a smaller piece, and now maybe in parallel you can do another smaller piece. I would think that would be a strong advantage to what you're suggesting, if it exists, but I don't know.
I'm not sure I understand the specifics, but
the question again is, what is the semantic advantage, the actual benefit other than syntax that you're causing, instead of passing the whole array and using indices? I mean, are you passing a subset somehow?
I mean, so in the end, in the implementation we've proven there is no array. It's only pointers in memory. It's really the pointer-based implementation. It's not array-based. So it's not the same implementation.
Which allows you to do more things.
Which could only, it does only.
That's the selling point. It allows you to do more things, not just another way.
I mean, that's a selling point for this specific implementation, if you want to have that. Yeah, yes.
Okay, somebody asked, well, how would you sell it? That's
In this case, well, you have to understand first that it's mainly a case study for Creusot, right? But also, there is one operation that you could do with this that you can do with the array, is that you can merge two unified structures together. With the array, it's not really possible, because once you've given away indices, you can't readjust them into the array,
if
right?
you lock an entire array, you can't share it.
Yeah,
If you lock a piece
kinda,
of it,
yeah.
Then you can, and I think,
Yeah.
I was hoping that's what you were saying.
I'm not sure it's exactly the same thing,
Okay,
but
so
yeah.
In the interest of time, and because we have one last talk, let's thank the speaker again.
Thank you.